Hello, everybody. Thank you so much for coming. We're going to make a big shift in gears right now. So systems methods, now we're going to go really molecular. And in particular, what I want to show you today, as I typically do, is try to make people start thinking about what are the neural mechanisms that underlie the adolescent period of development, a period that we are increasingly understanding is a significant time that will establish adult trajectories. I am particularly delighted to be in a symposium with my prestigious scientific colleagues and friends who are extremely creative in how they approach their science. And yeah, Facebook is very helpful. Ted, you need to up on your Facebook, by the way. We were all tasked with roasting one another, so I think we did good. So I want you to take a second and think about what adolescence is. And I just want to underscore some of the uniqueness of this period. Number one, this is a time when cognitive systems are available at adult levels. And they are being very much driven by heightened reward and motivation. And these two processes together allow for this time of the lifespan to be one of particular ability to gain new experiences that are going to be needed to specialize the system and to start to stabilize the system so that we can define adult trajectories. In fact, adolescence is a time when you start to see the emergence of mental illness. However, diagnosing mental illness in a definitive manner actually occurs after adolescence and young adulthood. So again, evidence that this is a time when there are neural mechanisms that are just dynamically specializing so that then they can stabilize. So the way that we've looked at development, and you might have heard me say this before, is that previous to adolescence, maturational principles are really about accumulation. The brain is growing, you're gaining new abilities. And by adolescence, everything is already there. And now maturation is shifted to a period of specialization, using Hebbian processes. You know, you keep what you use, you get rid of what you don't use. So what is specific to that ability to specialize? Now, last year in Singapore, I gave a keynote where I talked about all the different modalities that we use to really try to understand what are the mechanisms that allow for dynamic change. And today, I'm going to tell you about what we have been finding, the latest, which I did not include in the Singapore one because it is so new, using magnetic resonance spectroscopic imaging so we can start to understand some molecular mechanisms of developmental change. So this work is motivated by one of my favorite sorts of discussions in the laboratory with Bart Larson that led to a review paper where Bart scoured the literature, the post-mortem human and non-human literature, to look in molecular changes in the brain during adolescence. And interestingly, what we started to find were hints for critical period plasticity. I know that that can sound a little bit over the top, but in fact, here I'm showing you, typical work from Takao Hench, describing the principles of critical period plasticity. And they are based on the fact that excitatory, driven by glutamate, and inhibitory, driven by GABA, balance is shifted, opening critical period plasticity. So you're born, you open your eyes, you get this influx of visual information, not prepared for, so much excitation, and the brain will recover by increasing or, starting to correct that balance, reorganizing that cortex so that now that information can be processed in an optimal fashion. And then you get all the specialization of visual cortex. If you put these principles in the context of what is out there in postmortem human and non-human literature, knowing what we know about the adolescent period, we really start to understand that, wow, there's critical period plasticity that is occurring in higher order association areas such as prefrontal cortex, predominantly because that is the part of the brain that has been most studied with postmortem studies. In fact, what has been found there, when you look at the molecular aspects of GABA, of which there are many, you see that during the adolescent period, some have reached stability, other ones are increasing, other ones are decreasing. With glutamate, there is a recurrent finding that glutamate is decreasing through the adolescent period. So, in fact, showing us that there is a shift in that balance. And that is what we have been working on lately, is trying to test this hypothesis that there is a change in the rate of excitatory and inhibitory mechanisms during adolescence that might underlie critical period plasticity. So what we had to do to actually look at this in the best way possible was to go to 7T. 3T is great. People have been using spectroscopy for a long time. But the voxels are very large, and the SNR is very low in 3T. And if you're interested in things like GABA, and you can see in the spectrum, I guess I don't have a point. Oh, there we go. GABA, you can hardly see it in the spectrum. You need the highest level of signal-to-noise ratio to even be able to detect something like GABA. So 7T starts to approach that level that allows us to reduce the noise brought in by macromolecule contaminants. So when we think GABA, GABA is not just the synaptic exchange. There's free-flowing GABA and glutamate. So we really need a way to really focus and define the type of neurotransmitters that we can actually measure. And 7T allows for a better separation and quantification of these metabolites, not just for GABA and glutamate, but also for glutamine, which really allows us to dissociate, what is really about glutamate, what is really about GABA. The voxel sizes from going from 3T to 7T are more than 10 times smaller. So then when we actually apply using a slice approach, which you can use in 3T, but at 7T, we can get a whole slice with multiple voxels that we can start to assess differences in neurotransmitters. So what I'm going to show you today is data from now 71 10 to 29-year-olds. This is a longitudinal study with the goal of obtaining 170 subjects, but I thought it was time to start showing what we have been doing with this data. We use something called the J-refocused imaging sequence that has been developed primarily by my collaborators, Hobie Hetherington, who's one of the lead 7T spectroscopy investigators, and Julie Pan. And we were able to acquire the data so that we ended up with a matrix of 24 by 24 voxels. If anybody knows spectroscopy, this is pretty mind-blowing, with voxels that are 9 by 9 by 10 millimeters. If you're thinking fMRI, you're like, oh, these are huge. But in fact, we're talking millimeters in spectroscopy. So this is a huge advancement. And then the other thing that we did, because you want to be obtaining the same data from each subject, is, first of all, we decided that we wanted to angle it between the thalamus and prefrontal cortex because we're very interested in this whole frontal region. And then we developed a new freeware. If anybody's interested, you can let me know. We are calling it Kipasa. And here we are able to, within a scan, so the participant comes, we start to look at their brain. We can look in their native space on the MP range so that we can position the slice in the same place for every single subject. And then what we did for analysis, which is also, and a lot of these things are new. A lot of these things we've been, working in a big group with, physicists and so forth and statisticians to figure out what is the best way to take advantage of 7T spectroscopy. So one thing that we've done is that we identify coordinates in our regions of interest, and we maximize the amount of gray matter within each voxel. We want to look at gray matter not at white matter, which will undermine the spectra that we're interested in. We used an LC model, which is typically used. We also determined that, as is used across spectroscopy studies, that anything above a CRLB of 20 we excluded. We found that exclusions and inclusions of the data did not differ by age. I cannot emphasize enough how important in every developmental study it is to make sure that what you've excluded and included with regards to the quality of the data is not changing by age. We controlled for gray matter, for head motion, which was assessed by resting state scans. We controlled for gender and hemisphere. And then we modeled each ROI and neurotransmitter, and we FDR corrected for multiple comparisons. So here are some of the results. So I'm going to tell you about age-related changes in GABA and glutamate. We used a GAM model. This is also something that I encourage people who are interested in looking at age differences in developmental change to start looking at GAM, because GAM is flexible to look at curvilinear trajectories, and it is sensitive to semi-parametric effects and so forth. So first, this is what we can find with 7T when we're looking at the distribution of these neurotransmitters. Look at GABA. We see a lot of GABA in the lateral aspects of the brain, particularly in frontal regions. When we look at glutamate, there's a wider distribution, but it's also very lateral. So mid-frontal and subcortical regions have low measures, or in 7T, it's appearing as low measures of these neurotransmitters. But we also know from postmortem work that there's a lot in more of the lateral and cortical regions. So when we look at all the regions of interest in frontal cortex and ask the question, are we seeing these type of changes? What we found, and this was a little bit surprising because we had really predicted that there would be increases in GABA, we find that GABA is actually stable. And in fact, what we find is that the levels of glutamate are significantly decreasing. When I talk to my postmortem colleagues, they're not surprised. The emerging evidence from postmortem studies lately have been that critical perioplasticity is not so much driven by GABA, but actually by reductions in glutamate. So we're starting to get excited about this sort of a result. The important thing here is that the ratio is changing. Just keep in mind that the balance is what we're interested in. When we go into our regions of interest, so here we have dorsolateral prefrontal cortex, we find a similar story where GABA is established, but glutamate is significantly decreasing. And here you can really, see how the ratio has changed, how now glutamate is a lot lower. So the balance with GABA is being regained when you get into adulthood. In anterior insula, we are very interested in this because we're finding something that's even beyond this. We're finding not only is glutamate reducing, which we find continuously, but GABA is actually increasing. And we were intrigued by this. We're not completely surprised because we know the role of anterior cingula, the anterior insula, in cognition and how important that is during this developmental stage. And Lucina Uden, I don't know if she's here, she's done some fantastic work that we know. Anterior insula is critical for the salience network, for coordinating the interaction between default mode and executive network. So there's a piece of the puzzle is going on here that's really telling us that this plasticity is continuing. In the caudate, we see no changes in rate, just overall decreases in these neurotransmitters. In thalamus, we see no change in the ratio or in the measures. So this set of conclusions is showing us that in frontal association cortex, there is evidence for these changes in GABA and GLU ratios with age that are predominantly driven by changes in glutamate. Just a couple of more things. So when we look at functional connectivity, right? So these are these initial studies. How are these mechanisms affecting things that we know are changing with development? And what we're finding, and in our initial studies, is that greater neurotransmitter ratios are corresponding to less connectivity. And less connectivity, decreases in connectivity, is a predominant finding developmentally. We have, and I'll tell you about some of the posters that we're showing, in frontal striatal connectivity, this marker of specialization through development, of decreases in connectivity. And finally, we eventually want to understand how this is affecting behavior. And what we're finding, and these are controlled for age, the functional connectivity and now the behavior, and we're finding that there is an association between GABA and GABA-GLU ratios in performance in the spatial span and the CANTAB for working memory. And this is very important because we know that GABA plays a very important role in gamma oscillations, which are critical for the ability to retain information online during working memory, a process that continues to specialize into the 20s. So, in conclusion, we think that greater frontal cortex GLU over GABA measures in adolescents are suggesting a possible critical period plasticity that is supporting what we know about cognitive maturation, and that this might be critical to understanding how adult trajectories are being established. This is extremely novel data that has not been acquired before, so I hope that you're excited as we are. The next steps are, we had all these subjects come and also do EEG studies, because we want to know the impact of changing this ratio into SNR. So we have them do resting, sit, and working memory, and I'm hoping to update you the next time. Thank you to our awesome laboratory, particularly the work that Finn, Hobie, Victor, Maria, and Norma have done to help us, and Will, who's not here, thank you, and NIH and the Staunton Farm Foundation. If you like what you've heard here today, and I did ask my colleagues to show this slide. I see that they forgot. I encourage you to go to an offspring of OHBM, which is the Flux Congress, which is an OHBM that is focused on developmental cognitive neuroscience. It's in New York. The host is Nim Tottenham, and the program chair is Deanna Bard, so you know it's going to be fantastic. And finally, I'll encourage you to go and visit some of our other posters. Maria and Orma are going to be talking more about the 7T spectroscopy. On Tuesday, Ashley's going to be talking about our PET MR studies, looking at functional connectivity and the role that dopamine is playing through development. Finn is going to be talking about resting state connectivity in big data sets, including several longitudinal data sets, and what is the shape of trajectories, of developmental trajectories and how they're changing. And finally, Brendan Turbo-Clemens is going to be presenting some really striking meta-analytic data underscoring the role of the striatum as a risk marker for adolescent substance use. Thank you.